good afternoon, good morning, good night, and maybe good very morning, everyone. So it's a pleasure to be here. And I will try to illustrate what we do in our lab in trying to understand complex catalysis and in some relevant reaction that you may be interested in, such as propane dehydrogenation and CO2 conversion processes. So without further ado, let's start. And as we know, in catalysis, we have several classes of catalysts, being supported metal oxide, like this one, zeolite, and supported nanoparticle. And often, obviously, what we are trying to do is to try to improve this performance indicator, being activity, selectivity, or stability. And typically, we try to relate that to some kind of macroscopic thing that we can measure easily. And often, we often refer that to role of support, role of additive, promoters, role of size and composition, because the system is so complex, actually very difficult to relate to specific descriptors of the molecular world as you would do in homogeneous catalysis. Nevertheless, catalysis is a molecular phenomenon where you break and make bonds on an active sites. And ideally, what we like to be able to relate this performance indicator to specific structure or dynamic property of these active sites. So what I will try to do today, and what we have been trying to do in our work, is to look at this supported system across several reactions, going from this supported metal oxide with olefin chemistry and C1 chemistry. And we have done a lot of work with BP in that area, that I'm marking in green here. We also have worked a lot on zeolites, mostly nowadays working on the selective oxidation processes with TS1. And today what I want to focus on is this even more complex system, which are supported nanoparticles, and I will focus mostly on two types of reaction, either PDH or propane dehydrogenation, as well as selective hydrogenation. I will focus on basically mostly CO2 hydrogenation. And this will actually be these two reactions will help me to illustrate our approach to catalysis. So as I said, catalysis is a molecular phenomenon. We have an active site, and a big chunk of our work in our lab is, can we try to generate model active sites in complex systems? And the way we approach the problem in our lab is we try to generate a well-defined structure. So we develop preparation method to generate, if possible, a model less complex system. We develop spectroscopy tool to address the question of structure. We obviously measure property, and here we have a lot of effort in trying to evaluate basically catalysis in a more rigorous way. And then we apply a lot of computational tool to try to understand structure, spectroscopy, and drive basically the way we are going to evaluate our catalyst. And so basically we always do the same approach, and I will illustrate this approach via a very simple scheme. So as I said, the first thing we try to do in our lab, as we try to generate this type of catalyst, whether they are supported metal oxides or supported nanoparticle, we always start with a support. Typically, we use an oxide or sometimes in some cases carbon. But the first step is try to basically control the density of surface functionality, and in the case of oxides, that will be mostly OH group. So we apply typically vacuum under high temperature to generate a support where we're going to have an OH group, say, every nanometer. Why do we choose a nanometer? Because a nanometer is the scale of basically the molecular world. Then when we have this support, which has been tailoredly prepared, we generate a well-defined supported system using tailored molecular precursor that we graft on this OH group. And then from this well-defined system, which is actually very similar to homogeneous catalyst, because we still have a lot of organic ligand, we are going to remove this ligand either by some post-treatment under oxidative condition. And if you have with very early transition metals, you are going to generate isolated metal sites that will have the structure that depend on the ligand set that you have in this structure. While if you work with late transition metal and you work under reductive condition, you will start to cleave this metal oxygen bond, generate atoms that will basically at the end migrate to make a nanoparticle. And I'm going to show you today how we can use this approach to generate either isolated metal sites or basically a supported nanoparticle. So let's dig in the first case study. So propane dehydrogenation, we know it's a nowadays a very, very important reaction in industry because of the advent of shale gas and the need to basically do what we call on-purpose propene metathesis propene from basically propane. We know that this reaction is extremely endothermic, and the only way you can actually drive that reaction is by temperature. As you know, temperature brings some challenges in chemistry because temperature means that obviously you increase the rate of the reaction, but you also increase the rate of byproduct formation, and this actually typically induces problem of stability and selectivity of catalyst. In the case of propane hydrogen, there are basically, I would say, two main categories of catalyst. The Udry-Catofin type catalyst, which are basically supported chromium oxide on alumina, where people propose that chromium-3 is an active site. And then you have basically this more complex system where you have basically platinum in the presence of a promoter element, typically tin in the all-flex process, but also nowadays you see many other elements, in particular gallium has been shown to be an interesting system for this reaction. So I will show you what we have our contribution in that field by trying to understand this very complex system. So the way we started this work in our lab is we knew that gallium oxide is actually a very, very good propane hydrogen catalyst. The only problem of gallium oxide per se is that it deactivates very fast because it reduces, and as gallium oxide reduces, you basically switch off the activity for propane dehydrogenation. But we know very well that gallium zeolite are used in the cyclar process to convert propane to aromatics. And what people have proposed in the case of gallium zeolite is that obviously gallium is very important for the first step, propane dehydrogenation, but the second step is basically related to the conversion of propylene to basically aromatic compound via very exactly acid catalyzed reaction. So with that in hand, we said, can we somehow generate a well-defined gallium site at the surface of a material that will be able to do propene generation without doing oligomerization and trying to avoid basically to generate acidity at the surface. To do that, we got inspired for many years by the work of Professor Tilley at UC Berkeley. We actually have shown that metal siloxanes are actually a very nice precursor to generate isolated metal sites. So what we did, we took silica, which we treat at 700 degrees, where we have basically 1 OH every nanometer at the surface of this nanoparticle of silica, which are basically a very high surface area. We graphed this gallium compound, which turned out that it decomposed very fast to generate gallium-3 sites at the surface, which upon calcination generate isolated gallium sites, which are mostly tetracoordinated based on all spectroscopy that we could do, in particular gallium xanes and gallium hexaf. We could actually show that the gallium sites are isolated in contrast to what you have in gallium oxide, and that basically each gallium has, in average, 4 oxygen atoms in the environment, even though it's gallium-3. With that in hand, we obviously did propane dehydrogenation, and we could show that these gallium sites are actually quite selective and actually quite stable towards basically propane dehydrogenation, considering that if you look at the corresponding chromium system, the deactivation is actually quite fast, in the order of several minutes, and you always need to regenerate the catalyst during the reaction. Obviously, this has consequences. Actually, it's also some asset, because we know that in this regeneration process, you burn carbon and you generate energy for the process itself. So it's not always bad to have this fast deactivation. And obviously, chemical engineers actually use this as an opportunity to generate basically a reaction that can actually go on forever, or almost ever, so in scale of months to years in an industrial reactor. But with this in hand, it turned out that one of my very good friends, Bert Vekwizen, published a paper as he was working with Dow, where he describes that when you isolate gallium on alumina and you put platinum, you increase the rate of the reaction. And I found myself and my students the title provocative, because it was written platinum promoted gallium, which in a way means that gallium is the active site and platinum may not be the active site, which would be the contrary to what people may propose for platinum tin systems. So we decided to embark and try to understand a bit more what is the role of platinum and gallium in this system. And as we know, as soon as we go to a multi-metallic system, life will get much more complicated, because obviously you can have platinum nanoparticle. The platinum nanoparticle can be pure bulk platinum, but it can also be a platinum-gallium alloy, and it can make, obviously, many types of interfaces as you will generate your gallium oxide at the surface. So what we need to do is to use surface organometallic chemistry, where we're going to have a stepwise approach to generate our catalyst, where first we are going to put our gallium, and I've just shown you that indeed gallium can be generated at the surface of silica. Then we are going to graph a second component, here a platinum, basically, molecular precursor to generate this bimetallic system, where here we have a gallium highly dispersed at the surface plus a molecular complex attached to our surface. And then by a post-treatment, basically, we are going to generate platinum atoms, and our platinum atom basically will generate a nanoparticle. And depending on the system and how robust this isolated site is, either you will generate a nanoparticle of platinum with an interface of gallium oxides, or you will generate basically a platinum gallium basically alloy with basically some kind of interfaces. So let me show you the results. So what we did, we took this gallium silicate that I showed you before, where we have 1 gallium per square nanometer, and we have actually 1 OH per square nanometer, and we can graph a platinum compound to generate a bimetallic system where we have a grafted platinum atom and a gallium, basically, isolated site. Based on that, we can actually add hydrogen, and we can see that immediately you can see formation of nanoparticles, which are very small, which are in the order of 1 nanometer, which is actually quite small for silica. And when we put actually CO, we can see that CO is actually quite redshifted compared to CO adsorbed on pure platinum. So we know already that these nanoparticles are very likely not pure platinum, basically nanoparticle. With that in hand, we obviously immediately started to test our catalyst, and to our surprise and to our delight, I was very proud of this red data point, which is gallium siloxide, but you can see that without basically, with platinum, we generate a much more active and much more actually selective catalyst toward propane dehydrogenation. And in black are basically the same thing with platinum. So platinum is actually quite active, but only for a few minutes, because you may generate so much carbon that basically you deactivate the catalyst. Well, when you have platinum and gallium together, you increase the activity, you increase the selectivity, and you increase the stability of this catalyst. So it's actually very interesting to understand this system at a molecular level. So what we did next, obviously, we did a bit of spectroscopy, and we could actually show that in the process of growing nanoparticle, we definitely generated platinum 0. So you have very similar, basically, binding energy for platinum or platinum gallium system. But we can actually see that actually the gallium 3 of our support became mostly gallium 0 and got very likely alloyed in the nanoparticle, and you have a small amount of gallium 3 remaining at the surface of the support. With that in hand, we continued and did basically more detailed spectroscopic investigation, and we could actually show that the system is actually quite complex, and at the time we could not fully resolve the structure of this system, and then our particles are basically an alloy, but not an homogeneous alloy. What we could actually show is that very likely when you have platinum and gallium, you have a gallium-rich surface, basically alloy, where a core of platinum. That's actually what EXAF could tell us. And without going into much detail, the way we could actually improve the structural resolution or characterization is by combining our EXAF data with ab initio metadynamics, where we could actually optimize by free energy calculation the structure of a nanoparticle on a surface of silica, and we could show that indeed when you have a nanoparticle of platinum gallium 1:1, gallium has a tendency to migrate at the surface of the platinum and to accumulate also at the interface with silica. So in that way, what you end up having is actually some isolated platinum atom which are basically dispersed in some kind of gallium 0 sites. And with that, we could actually also show that in contrast to platinum, which remain crystalline, this is a case of platinum on carbon, even though it's very, very small. When you go to actually platinum gallium, I showed by this, metadynamic calculation, you can show that the system is much more dynamic and mobile. And you can see that basically, let me drink a bit of water. You can see that also by microscopy that you actually lose quite a bit of crystallinity when you introduce gallium in your platinum system, which is not fully surprising because we know that Small particles are typically much more amorphous than large particles, first of all. And second of all, we know that gallium itself is a liquid at room temperature. So by introducing gallium in platinum, you would expect to decrease the melting point of the system. With that in hand, we could actually show by a classical periodic calculation that the role of gallium is effectively to isolate platinum site, and you don't actually so much actually improve the CH activation step, but what you do very much is that if you compare pure platinum to platinum gallium, you basically improve basically the desorption of your propylene, because actually propylene on the platinum gallium is very destabilized, and it will probably also help basically with the activity of the catalyst, but also prevent a deeper dehydrogenation to propyne and to carbon, which is one of the problems of platinum. So let me switch gear now and actually try to go to a second case scenario, which is the CO2 hydrogenation. So we know that today, the way we make methanol is we basically hydrogenate CO with hydrogen, and this syngas is obtained by basically reforming of methane. And we know that basically today, if we look at this reaction to make methanol, we produce roughly 1 kilo of CO2 per kilo of methanol produced. And we know nowadays that one of the great concern is how to basically combine CO2 capture and conversion. And it has been foreseen that CO2 hydrogenation could be one way to mitigate CO2 basically increase in the atmosphere. And indeed, if you could actually combine CO2, and so you could actually do CO2 hydrogenation with green H2 coming from basically alternative energy, you could actually generate a process where you can actually generate methanol with a negative value on basically on global warming by basically removing 1 kilo of CO2 per kilogram of methanol produced. And methanol, as we know, is a very large-scale commodity chemicals as well as a potential fuel additive. So with that in mind, we actually came back to actually what we know how to do in our lab is trying to understand, what are the effect of component in a catalyst for the CO2 hydrogenation. And what we knew, obviously, is that in the syngas technology, copper zinc oxide with alumina are the basically workhorse catalyst for CO hydrogenation. And we also know that this same catalyst is actually quite good for CO2 hydrogenation. The only problem is that it often deactivate with time and has some issue with selectivity. What was interesting to us as chemists is to understand in a greater detail this support effect. So I knew from my former colleague, Professor Biker, that the support has a huge influence basically on basically the selectivity of the reaction. For instance, if you take copper and silica, and here we compare system where particle size are actually quite similar, at the exception of copper and titanium. And I will come back to that at the end of my talk. If you have copper and silica and you actually do CO2 hydrogenation, you typically always make methanol and CO with a roughly 1-to-1 mixture. As soon as you go to zirconia, you increase the rate of CO2 hydrogenation and you also increase the selectivity. While when you go to titania, you basically switch off the selectivity towards methanol to favor CO production. And when you go to alumina, you promote the reaction, but you promote all possible reaction, methanol formation, CO formation, as well as dimethyl ester formation, because obviously alumina is a very well-known dehydrogenation catalyst. So here you actually promote all of them together. So with that in mind, we said, can we try to understand what is the effect of the support in this type of system? And again, coming back to my slides, the question obviously that we want to understand is, what is the role of the support, the promoters, the defect on the overall basically reaction pathway. And what I wanted to do is to actually use our approach of surface organometallic chemistry to tailor the interface and the composition of our catalyst. So what we did first is to take a silica nanoparticle with the same surface area and to basically dope this silica with zirconia and use this dope support to grow copper nanoparticles. The advantage of this approach is we are going to have a very high surface area support, and in all support we are going to generate copper particles of the same size, which will be basically in more or less important surrounding containing zirconia. And with that, we could actually show that as we put more and more zirconia, the CO formation rate remained quite similar, while as you put zirconia, you actually increase the rate of methanol formation. So there is no doubt that indeed zirconia trigger the formation of an interface which basically promotes the CO2 to methanol conversion rate. So with that in hand, we said, let's try to simplify further the system and actually go to basically copper on zirconia as the actual system and try to approach and try to understand this system by combining DFT calculation, in situ IR, and ex situ NMR spectroscopy. Again, I will make a long story short. What we were able to show is that if I take a very simple system like a copper particle on zirconia, we can immediately see that if you do calculation, your copper nanoparticle, even though this one is a very small particle of 38 atoms, don't forget it was done more than 7 years ago, where it was actually still challenging to do this type of calculation, we see that the particle remains quite intact and doesn't want to basically wet the surface of zirconia. What is probably more interesting is that if you compare the C2 adsorption on copper 111, zirconia, and copper zirconia, you realize, not surprisingly, that CO2 does not interact with copper 111. It does interact strongly with zirconia to make a carbonate, and there is nothing surprising for us chemists. But what is actually surprising to us is that when you actually put CO2 at the copper zirconia interface, you actually make a very strong, basically, stabilization energy, because you transfer one electron to copper to CO2, and this formerly CO2 minus is stabilized at the interface by the Lewis acid site. So it was kind of interesting to see that this copper zirconia interface is quite a nice place to activate CO2. And in fact, we could show across many possible activation pathways that the interface is very favorable to activate CO2, and then you can actually cleave H2 on copper, and then H2 spill over, if you want, to the CO2 to generate formate, formalin, and methoxide. And actually the rate determining step in that process is the desorption of methanol to make of methoxine to methanol and methanol in the gas phase. And we could actually show that indeed this intermediate formate and the methanol are indeed, you can actually see them by IR spectroscopy. I will not show you that today, but you can also see them by NMR spectroscopy. And by multiple labeling experiments, we could actually show that indeed the formate is converted to a methoxy intermediate. But what was interesting to us, if it is true, what you actually need is a copper nanoparticle with an interface where you can actually stabilize this CO2 adduct, and what you need is basically Lewis acid sites. So we went back to the drawing board and decided to tailor a support to promote that reaction. And what we did is to dope silica with zirconium, isolated site, using a typical zirconium molecular precursor, and then graft copper and grow copper nanoparticle. And we could actually show that by doing so, we can generate, quite a narrowly sized distributed copper nanoparticle of roughly a bit less than 3 nanometers. And we could show that they are indeed copper nanoparticles. We could actually show that they remain isolated zirconium site, and that these zirconium sites actually promote methanol formation similarly to zirconia. And we could also see this reaction intermediate like zirconia. So we can show that indeed we don't need zirconia per se, but we need actually some Lewis acid site at the interface with our copper nanoparticle. What was interesting to us in our case, coming back from molecular chemistry, is what titania was so different from zirconia. Obviously, we know that titania is a big difference between zirconia and titania, is that titania is actually a wide band semiconductor and can easily make defect. And it turned out that when you have titania, one of the issues under CO2 hydrogenation condition is that actually you have to grow particles to make particles of 1 micrometer or so, which are basically inactive in CO2 hydrogenation. And actually what actually lead to activity of copper on titania is titania itself, which by having defect basically promote the reverse water gas shift reaction. So what we said is that if titanium is a good Lewis acid, we actually don't need to have titania. And why don't we try to generate a copper nanoparticle with a titanium isolated site by using basically this grafting, thermal decomposition, and growth of particle approach. And when you do that, you realize that indeed now you generate a very active and very selective catalyst, which basically shows that the problem is not titanium per se, but to have actually basically a wide band semiconductor like in titania. So if you can actually make titanium isolated into an insulated support like silica, it actually can help to activate CO2 to make methanol. And in a way, it relates to what we said earlier with gallium on silica for PDH. In the case of gallium oxide, we could show that it reduces very fast and lead to a poorly stable catalyst. When you have actually gallium isolated site in silica, an insulator, you can actually keep activity. So you can see there is a relation between the two systems. With that in hand, we actually went to a much more broader type of system, and we also studied basically gallium and zinc, which are the typical promoter of CO2 heterogeneation. But in that case, we could see that you make actually much better catalysts. They're actually much more selective at high conversion, which is actually what you want to do. And we could actually show that in that case, you actually make alloy. So you always generate copper, gallium, and copper zinc alloy. But these copper, gallium, and copper zinc alloy, and I will not show you that today, under CO2 hydrogenation, revert back to some kind of copper gallium oxide interface and copper zinc oxide interface. And often in the case of zinc, you still see a little bit of copper zinc alloy. But I will not go into more detail with that. To show you something that we did next is trying to see, can we actually look for new support to generate basically novel interfaces? And we were interested by a novel class of material, the so-called MXene, and we were able to basically make MXenes and disperse this medium oxycarbide at the surface of silica and generate basically, our goal was to generate copper nanoparticle. However, very fast we realized that when we do this system, if you look at our EDX MAC, everything is highly dispersed and we have no evidence of formation of copper nanoparticle in contrast to what we have seen in all our material before. And it seems that if when you do advanced microscopy study, all the copper actually migrate to the MXene and generate basically, it seems, single atom of copper at the surface of MXene, and the single atom of copper are enough basically to promote the CO2 to methanol synthesis. And again, without spending too much time on that system, we could actually show that in the case of MXene and a single atom of copper, this single atom of copper is good enough to hydrogenate, to convert CO2 into methanol by making basically all the intermediate I discussed before at the interface in this, well, I don't know if we can call that an interface, but between a copper basically atom and this MXene interface. So coming back to that, what I've shown you so far is that we can indeed use our SOMC approach to generate either a particle with a specific interface or a copper alloy. And what we wanted to do next is to see if we can actually explore other type of systems which are not known for CO2 hydrogenation. And I had a very, very good student from Britain in my group, Scott Docherty, who actually decided to investigate other type of systems. So we started to investigate palladium as a potential system for CO2 hydrogenation. Not that we believe that palladium is going to replace copper. We knew from the work of Shock and Love that nickel can be an interesting catalyst for CO2 hydrogenation. So we said, let's try to do what palladium will do. So we knew that palladium was a very bad catalyst for CO2 hydrogenation because typically pure palladium is poisoned basically by CO. But by using our approach, we could actually generate very small particles, and we could show very fast by our spectroscopy and EXAV that we generate this palladium gallium alloy. And it turned out that this palladium gallium alloy have extraordinary reactivity and selectivity towards methanol formation. They outperform by far copper, and you can see that they totally change the reactivity of palladium nanoparticle by having gallium incorporated into the system. So here we highlight the fact that basically we can move from a system which was totally inactive or hardly active for CO2 to methanol synthesis to something extremely active by having basically an alloy formation. We did a lot of study and we could actually show that by EXAV that actually we do have actually a palladium gallium alloy, and that as you pulse going from pure H2 to H2CO2, we see that the gallium gets actually oxidized partially under CO2 hydrogenation. And actually this is actually quite reversible. And this match basically the formation of formate of methoxide at the surface of the system. And in fact, if you combine EXAF and IR spectroscopy, we can see that indeed, as you have CO2, you basically make more and more methoxide. When you have CO2H2, you make more and more methoxide. And when you have pure H2, you actually remove the methoxy and you promote the formation of formate, which obviously requires also H2. So it seems that there is some kind of the dynamic between alloying and de-alloying, and this actually somehow correlate, and this is something we are still studying with the methanol formation rate. Next, and I will not go into any details, we went to ab initio metadynamics to understand a bit better this palladium gallium system. And to make a long story short, what we could actually show is that in contrast to platinum gallium, palladium gallium actually, the palladium gallium nanoparticle actually do not interact very strongly with silica. And we could show that CO and H actually absorb mostly on basically palladium topsides, and that basically all seem to point towards the formation of palladium gallium oxide interface to promote CO2 hydrogenation. And we believe that the role of gallium is to prevent formation of palladium island, which will be poisoned by palladium, while gallium oxide promotes very likely the methoxy formation rate, and thereby the methanol formation rate. With that in hand, we actually went back to our platinum-gallium system, and we could show that in contrast again to pure platinum, platinum-gallium on silica actually also promote methanol formation rate. And that actually, if you go from silica to carbon, you increase dramatically the CO2 formation rate, and now you have surprisingly a platinum catalyst, which actually is a very good methanol synthesis catalyst. Again, here I'm not promoting to anyone that we are going to switch copper to platinum. It's just to see at a fundamental level that as you introduce a promoter, you can fully change the reactivity of basically an element like platinum. And in fact, moving forward, we decided to screen all the precious elements, and we could show that indeed all the typical catalysts known for methanation, like ruthenium, osmium, rhodium, rhodium, iridium, which are very well known to promote methanation with under CO2 hydrogenation. As soon as you put gallium, they all become actually selective methanol, basically synthesis catalyst. And by going into much detail, we could actually show that in all of these cases, what seems to be very important is to actually always generate an alloy. This alloy is now stable under reaction condition. That's why you actually prevent methanation reaction, and you always have under reaction condition formation of an interface with gallium oxide, which seems to promote methanol formation. So we believe that this system are actually quite interesting in trying to understand basically what actually promote methanol formation rates. So by screening element, at one point working also with BP, we actually found that actually a typical element like iron, which actually typically used in Fischer-Tropsch or in water gas shift, you can actually start to generate platinum iron nanoparticle the same way that I've shown you with platinum gallium element. You can make very, very small particle across a range of composition, and that clearly as you put a one-to-one mixture of platinum and iron in a particle, you make extremely active and extremely selective reverse water gas shift catalyst, which can reach very equilibrium conversion at a rather low temperature quite efficiently. And in fact, they having the right amount of iron actually seem to help to minimize the activation energy of the CO2 to CO conversion process. And now going back to in situ infrared spectroscopy, we could show that actually the platinum and platinum iron are totally different systems. So for example, if I have platinum and platinum iron, you can see that if I pulse CO2, platinum does not activate CO2, while platinum iron immediately makes CO. And as you basically pulse H2, only platinum now makes CO, while the other one remain a normal water gas shift catalyst. So clearly, having iron and platinum together fully change the reactivity of platinum, and we believe what is happening is by having iron, we actually activate some kind of redox process between platinum iron and platinum iron oxide interfaces, which promotes water gas shift reaction. So I hope I've convinced you that with our approach, we can generate many complex systems. Today, with having explored more than 100 catalysts by this approach, I didn't show you all the details today. We can see that basically very likely metal oxide interface play a very important role in driving methanol formation. We also see that this involves redox processes. Very likely the metal remain metallic and the promoter element like gallium always switches between gallium and gallium oxide. And we believe today that very likely gallium oxide is very important to accelerate methoxy formation rates, while going back to gallium metallic will help to dissolve methanol, which actually is a rate determining step in methanol formation. However, obviously, we don't fully understand fully the role of these redox processes, even though, as I told you now, we have some idea. And we don't really understand the kinetics of the redox process and how this kinetic of the redox process is related to the overall kinetic of methanol formation rates. And we are still looking for a better predictive, basically, reactivity descriptors. And towards that goal, we have embarked into the last part of my talk, which is to actually explore broadly the chemical space by using high-throughput experimentation. So I will want to show you in the last few minutes our new venture into basically incorporating what we call data-driven high-throughput experimentation. So as we know, if you start to have many parameters, the big problem is that you start to have an explosion of the chemical space. Because if you have already 2 or 3 elements in any type of possible composition, and you start to have several types of support, you can have several types of loading, you can have promoters, you easily reach many millions, basically, possibility. And here I will show you one example where we were trying to set up a benchmark system on methanol synthesis that we need to find some ways to accelerate our basically exploration and to get a very good data point. So to do that, what we have done is to combine Bayesian optimizers and basically automated the library of for synthesis and catalysis testing, using basically typical support used in a CO2 hydrogenation, typical 3D element and promoters, and try to see, let basically the computer decide for us how to explore the chemical space. So this was not fully unbiased because, we started with a series of knowledge, but the computer itself is unbiased because we only gave him the possible composition and chemical space, and the computer basically, by this Bayesian optimizer, basically propose composition as we make the catalyst propose. We typically make 28 catalysts at a time, test them, and based on the results, we basically go through that circle. I will show you basically what happens through 5 iterations to show you how powerful can be Bayesian optimization to explore basically chemical space. So as I said, we started by a fully robotized system to basically prepare solution of basically metal element, disperse it into making our support, disperse it and dry our system, fully barcoded to track the reaction across all the possible time. And the slow step, as you know very well, was to put basically the catalyst into the actual reactor, which was then tested for CO2 hydrogenation. So let me show you the results that we obtained after the first generation. So after the first generation, you can see that the color represents basically all possible composition and support. And we can see that for the first generation, we see basically most of the catalysts do not perform very well, neither of methanol formation rate nor in CO2 conversion. You can see one catalyst which is very good to convert CO2, but basically is not very selective. And there is one catalyst basically that looks like it's a bit more selective than the other. And then we actually try to do a basically optimization parameter where we try to optimize CO2 formation rate, minimize basically methanol formation rate, maximize methanol formation rate, and minimize cost based on the cost of metal. Okay, and this is basically our performance indicator to basically drive our optimization process. And then after the third generation of catalyst, we generated a new generation of catalyst proposed by the Bayesian optimizer. And you can see that obviously very fast the Bayesian optimizer actually has identified, and you can see that it's not unbiased, copper-based catalyst. Okay, and immediately you can see that you improve dramatically methanol formation rate, CO2 conversion rate and methanol formation rate, and you decrease basically the cost of catalyst while minimizing methane. And you can do that across many generations, and the catalyst actually very fast populate the chemical space. And you can see that at the end, you actually end up with catalysts that contain a lot of much lower loading of copper because you are decreasing the price. And you can basically start to see appearance of elements which are not typical of basically CO2 hydrogen synthesis, conversion of CO2 to synthesis methanol catalyst. So with that in hand, basically, within 5 weeks, we were able to actually obtain catalysts which, in terms of activity, were as good as the best catalysts that we have produced in our lab in the last 5 years, which shows that, in a way, the efficiency of using baseline optimizer to basically develop system. But what actually was most striking to us is that we told our basically algorithm after 5 iterations what would be the catalyst, the ideal catalyst, if now that you know all this data, if we had no constraint of cost. And you can see that immediately after the other generation that actually picked up for the first generation contained only indium. So you can see that basically with one system, he basically find another set of catalysts which are much more selective, slightly less active to convert CO2 into methanol. So we believe this approach of high throughput testing combined by Bayesian optimization is actually a very interesting approach to basically try to basically accelerate the rate of discovery. And what we are trying to do now in our lab, and I will have no result to show you, but this is an approach that we are now using, is to combine basically this data-driven approach with the earlier approach that I've shown you in my slides, combined with computational chemistry, to basically incorporate and identify key chemical descriptors obtained on the one hand by spectroscopy and by theory, trying to actually understand at the molecular level how these catalysts work, and hopefully have actually a guideline principle to design better catalysts. So I hope today I've convinced you that indeed with SOMC we can try to understand basically a catalyst one atom at a time. And I remain to thank the people that did the work. What I've shown you today was developed earlier by Keith Searles and basically Lucas Leitch with here for the propane hydrogen catalyst. And all the CO2 hydrogenation was first started was Keith Searles and basically Kim Larmier and Hervian Lam, and now are continued by Weizhu, Colin, Scott, and Chao Yu, which actually were partially sponsored by BP to explore the CO2 hydrogen catalyst. And with that, I remain to thank you very much for your attention. I'd be more than happy to answer your questions.